Our next speaker is Clara Brasseur, who's from the Mikulski Archive for Space Telescopes, MAST at the Space Telescope Science Institute. And she's going to talk about listening to the stars, Astronify, using sonification to get more details out of the data. So Clara, you can take it away.
All right, so today I'm going to talk about a new Python package called Astronify that is for data series sonification. I'm the person giving this talk, but this project is very much a group effort, and we have a core team of 4 people and then are working with too many other people to name today. So what is sonification? The concept behind sonification is simple. It's just representing data as sound. And there are a lot of different ways to do it and a lot of different reasons to do it. But what we are primarily looking at in this project is how to translate light curves into sound in a way where it can be scientifically analyzed. So this is a stellar flare sonified. And Jessica, can you confirm that I properly shared my audio and you could hear that?
Yeah, it came through just fine.
Great. So there are a lot of, as I said, there are a lot of different reasons for doing sonification, from scientific reasons to more artistic reasons, to adding different dimensions. But the core driver behind this project is to increase accessibility, particularly to blind and visually impaired astronomers and future astronomers. And this project is one part of a larger sonification community, and we've been very involved in trying to bring together different people, specifically looking at sonification for astronomy. So there is a monthly sonification world chat that keeps growing. It currently has about 50 people, really from all over the world, so we never get all of the people at once. And we've also been working from the very start with blind and visually impaired scientists and developers, since that is our main goal, is to be useful to those people. We clearly need them to be involved from the beginning, so we're not just writing in our own little bubble. And we're also very excited that there's going to be a Splinter meeting at the upcoming AAS meeting about sonification. So anyone who's interested or is already involved in this work, please talk to me or anyone else and get involved in these things. It's great. So the vision for this particular piece of software was for it to be open source, community driven, and easily integrated into a standard scientific workflow. So the code is on GitHub. The documentation is on Read the Docs. It can be installed locally, and you can easily change, modify, see all the code. So that part is great. It isn't quite, it is open for issues and pull requests, but the initial release is very close but not quite there. We're working out a couple of kinks in our testing infrastructure, and then it will be released, and at that point we will really be able to consider ourselves stable enough to really start soliciting contributions from the community. This is a very new software program. And in some ways, it is already from the start easily integrated into scientific workflows. That was the main driver behind using Python. It is the most popular language in astronomy, so astronomy students and professional astronomers will already be using Python, and then this is just part of that. But because we are part of the MAST archive, we want to go one step further and make this an option right along with the normal or standard give me a FITS file. Instead, give me a sonified file when asking for data from missions like Kepler and TESS that produce light curves. So the design of the software itself, as I've mentioned, this only sonifies data series right now, and so we designed the software to be modular. So currently this is what is there. The main class is the Soni series class that takes in all of the information needed to sonify a data series light curve. And then in future, it would be great to be able to expand to things like spectra, images, all other kinds of data. And so this series class has a data table member. So this is where the user gives in the actual light curve data. And then there's some information that is used to determine how the sonification occurs. So there's a function that takes data values, intakes data values and puts out audible pitch values in hertz. And then there's some sonification parameters that determine exactly how that happened. And all of these things are used by the workhorse function, which is the sonify function. And that function also puts back the sonified data before it's actually played into the data table. So you can always look at this manually. And then there are two options once your data is sonified. One is to write it to a WAV file on disk, and one is to play it right within your Python interpreter. So what does this look like in practice? Well, here's the all-important Soni series data class. And it doesn't really take that many lines of code, so we can build a small test data table, and without giving it any other information, that means that the Soni series object will use the default sonification function and parameters, and then we can call the sonify function, and now we have sonified data. So if we look at the data table kept within the object, there's the original time and flux columns that we gave it, and now there are two more columns, Astronify pitch and Astronify onset. So pitch, these are all values in hertz. The human ear can hear between about 20 and I think 20,000 hertz, but for comfortable listening and also because of computer speakers, you want to stay much closer into a much smaller range. So these are all comfortably audible by human ears. And then the onsets are how long after the start each pitch will be played. So then we can call play and hear the sound. And when you do call play, you don't get a plot like I'm showing over here. I did have to put that together manually. You'll just hear the sounds. So this plot is plotting the flux versus time. So those are original data data columns that we put into the object, and then the red cursor will track the play. So that was very short and fairly uninspired. And this is because we didn't actually change any of the defaults. So if we look closer at what the defaults are by printing some of these parameters, we can see that the default time between notes is 1/10 of a second. And the reason that that's the default is that usually when you're sonifying real data, you've got hundreds and thousands of data points. Think about a Kepler quarter long cadence data curve. There's like several thousand data points. And so if you want to not feel like you're actually watching a transit, a planet transit, a star in real time, you need to bring the time down. And then each individual note duration is 1/2 a second. So this is why we also get that chord sense. They're overlapping. So we can change these, and we'll take that note spacing up a lot, and we'll take the note duration down just a little bit. So now we can hear the whole thing more clearly. And so we can see in the onsets column that now we're getting 0.2 seconds between notes. And if we listen, it sounds fairly different. So now we can really hear that nice rise, and we can hear the individual notes. But these aren't the only things that we can change. We also use the default pitch mapping function, which is called data to pitch. And it takes in the all-important data array. And it also takes in a number of arguments that all have defaults that we have determined to be sane, basically empirically. And these are the default arguments. So what this is saying is that the output is going to be between 100 and 10,000 hertz. The median of the data will be mapped to 440 hertz, which is the A above middle C for any piano players out there. And that the stretch of the notes will be linear. So we are going to match the stretch. It will be mapped linearly across. And so these inputs are very much like the inputs, and in fact are very much based on the inputs that you would give to an image manipulation function where you're putting in your actual like electrons per second from your FITS file, and you want to get out something where you can see the features you want to see. And like images, there are reasons that you would want to do it in different ways depending on whether you're like looking at bright stars or the faint limbs of a galaxy or anything else. So if we change these somewhat, so we're going to add some clipping. If we have min-max value, we will clip the upper and lower bits to 2 and 8, and then we're going to bring up the bottom of the pitch range and then move the center pitch up an octave. So we should be able to hear some pretty major differences in the new sonification. And now I've switched to mapping pitch versus time instead of the original flux, so we can really see how this changed. And we can see that we do still have this linear rise, but we now have flat tops and bottoms where we've clipped our values. And then if we play it, we can hear those flat values because of the clipping, and we can also hear that we're definitely getting higher notes, which is great. These are all of the things we set. And so let's play with the stretch now. Depending on what parts of your light curve have different features that you want to hear, you might play around with this. So I'm going to set the min-max value back to none, so we no longer have clipping, and then set the stretch to log. And so looking at the plot now, we can definitely see that this is now because we're mapping pitch instead of the flux. We can see this log shape, and we can also hear it very clearly. So there's a big gap at the beginning, and then it follows a logarithm, and it gets closer together at top. So that's all great, but that's really just test data. So what happens when we actually sonify real data? So here I'm pulling in a test light curve, or building a test light curve using the light curve with a K package. And I'm going to limit myself to about 500 data points, basically just so that it doesn't take as long to listen to. And I'm going to set the parameters the way I want to hear certain features. So I'm taking the note duration down a little bit, but I'm taking the note spacing down a lot. So this is going to scan through the light curve significantly more quickly than default. And the reason I'm doing that is what we're looking at here is the light curve from a heartbeat star. And so with that really fast scan, this is what it sounds like. So I'll play it again in a second, but what you can hear in this sonification is you can hear these large scale features where we have this sort of larger scale periodicity where the range gets big and then gets small. But less can we hear these little, there's all of these little sinusoidal type things that are going on, and they are just all mushed out because we've got this overlapping. We just hear these beating chords. So we can really hear the heartbeat, but we can't hear the small scale structure. So we can change that. So now I'm going to keep the note duration where it was, but I'm going to take the note spacing up by an entire power of 10. And again, I'm just going to sonify even less of the light curve simply for timing reasons. So here we can see that we've more or less zoomed in on this light curve. And we're going to scan across a lot more slowly, so we get, instead of what we heard before, so now we have to wait a lot longer to actually hear this large scale, and it's not as obvious because we're not hearing that fast beating, but we can hear what's going on at a smaller scale. So it depends on what information you're trying to get out, how you're going to want to set these things up. So that was just a brief introduction to this software. Everything you need to know about it can be found on astronify.read the docs. There's lots more examples. There's a test you can take if you're interested in seeing what features you can hear. You can also email us. And if you're coming to the AAS meeting in January, definitely would love to see you at our Splinter session.
Okay. There's one question from Jan Grange. Are there any data repositories around that people can use to make sonifications of paper figures available and linked to the original paper?
Okay, so no, not that I know of. So I know that there is a group in the sonification world chat that is focusing on specifically plot sonification, with their goal being that you can basically feed any plot into it and get a sonified version out. I don't believe there's currently any data repositories. One thing that we are working on and that is in the works is collecting information from all of these projects into a central web page where you can scan through and for your use case and see what's being done. So if you're interested in that, email us, and when it's available, we'll send it out. And I do know there is a group looking at specifically paper plots.